Here is the stoichiometric calculations. In this video, we're going to talk about mole concept, types of chemical reactions, and calculations based on chemical reactions. Let's start with the mole concept. Now, 6.02 times 10 to the power of 23 was named after Amedeo Avogadro. That's why it is known as the Avogadro number. Any substance that contains Avogadro number of particles is known as 1 mole of that substance. So when relative atomic mass of an atom or a molecule is given, you should be able to write two sentences. The first one, for example, carbon is given as 12 here and oxygen is given as 16 here. This means 1 mole of carbon atom weighs 12 grams. Or you can have another sentence, only 1 carbon atom weighs 12 grams per Avogadro. Now, this is known as, this gram per Avogadro has a shortcut name, which is AMU. Remember, it is atomic mass unit. So when I say, or when you're given carbon is 12, then you should be able to tell that 1 mole of carbon atom weighs 12 grams, or 1 carbon atom weighs 12 grams per Avogadro, or 12 AMU. So AMU is a really small amount. So this can be written not only for atoms, but also for molecules. For example, carbon dioxide molecule. If you calculate 1 mole of carbon dioxide is 44 grams, or if you have only 2 carbon dioxide molecules, I'm really talking about here small amounts. This is going to be not 88 grams, but 88 AMU. Now comes the types of reactions. The first one is redox. In redox reactions, electron transfers occur. Now, what is the meaning of this transfer? One atom or ion should gain an electron while the other one should lose that electron. For example, the oxidation number of iron is here 0 because it is in its elemental form. So it becomes 2 plus after the reaction. Now this means that it gives away 2 electrons. Now next one, this is copper 2 plus, and after the reaction it becomes as copper 0 here. So this means that this is gaining 2 electrons. Now as you see, the number of gained and lost electrons should be equal to each other. So in this case, iron is said to be oxidized and copper 2 plus is said to be reduced. Now, if a substance is oxidized, this means that it should reduce the other one. So if iron is oxidized, it is known as the reducing agent, where the copper 2 plus is known as the oxidizing agent. Combustion reactions, they are usually known as reaction with oxygen gas. The reaction that produce heat and flame, but I wrote it as generally here. Sometimes there are some combustion reactions, but they do not produce heat or flame, but these are generally known as the combustion reactions. And when an organic compound, now organic compound means it mostly have the carbon atom and or hydrogen, oxygen, etc., sometimes sulfur and nitrogen. When they are burned with the sufficient amount of oxygen, carbon dioxide and water molecules are produced. And if you have nitrogen, for example, it can produce nitrogen dioxide. If you have sulfur in it, it can produce sulfur dioxide. It depends on the types of the organic compound. These are usually exothermic reactions, meaning heat is given out. Exception is the nitrogen gas, because 2 nitrogen atoms have triple bond between each other. So this means that you really need to give high amount of energy to break these bonds up. And some elements and compounds are inert for combustion, like sulfur trioxide, carbon dioxide, or you can say helium, or you can say argon. Now, it's easy to understand why helium and argon are inert for combustion, because they are noble gases. Now, what about sulfur trioxide and carbon dioxide? Now, when I write sulfur trioxide and when I just calculate its oxidation number, I calculate it as plus 6. Now, remember, sulfur is in the group of 6A, and plus 6 is the highest oxidation number that it can get. So you can no further burn that sulfur trioxide. There is no such a reaction, sulfur tetroxide. So this is not true. And the same thing is valid for carbon dioxide. When you calculate the oxidation number of carbon here, it is plus 4. So when you like to burn it, it cannot have the oxidation number of 5 plus or 6 plus, because it is already in the group of 4A. So you cannot burn it. So there is no reaction. That's why we call sulfur trioxide and carbon dioxide inert for combustion reaction with oxygen. Acid-base reactions, and you should really be careful with the acid-base reactions. Usually you know that acid-base is just directly the neutralization reactions, but not all the acid-base reactions are the neutralization reactions. Of course, there are exceptions. In chemistry, we have a lot of exceptions. Neutralization reaction can take place if and only if hydrogen plus 1 reacts with the hydroxide minus 1 and give you the water molecule. So this is the necessity of neutralization reaction. This means that acid and base should be dissolved in water. So that aqueous means here aqueous solution. Sometimes we write it as aqua here. This means that they are dissolved in water. So this is really important. So when they dissolve in water, hydrogen ion and hydroxide ion just become free and they combine to form water molecule. Dissolving and precipitation. For example, when you put sodium chloride into water, you write the dissolving equation like this. Sodium chloride solid, and on the arrow you write the water here, and then it produces sodium plus 1 aqueous plus chloride minus 1 aqueous. Sometimes vice versa of this reaction occurs. This is called as a precipitation. But first you have to be really know the solubility rules. For example, most nitrate salts are insoluble in water. They do not give that precipitation reaction. The salts that contain alkali metals and ammonia, they are also really soluble in water. Not only the nitrate, but if the salt contains acetate ion, this gives the salt a really high solubility. Most chloride, bromide and iodides, they are soluble, but if they combined with the transition metals like silver, lead and mercury, they become insoluble. Most sulfates are soluble, but when they have the cation barium, lead, mercury, strontium and calcium, they become insoluble. Most hydroxides are insoluble, but if they have that alkali metal, sodium, potassium, then they are all soluble. Most sulfides and carbonates and chromates and phosphates insoluble if they don't have that group 1A metal, alkali metal with them. Now, the main part of this topic is the stoichiometric calculations. Let's start with an example. For example, here is the combustion reaction of ethylene here. First, balance the reaction. You have 2 carbons here, so you have to put 2 in front of carbon dioxide. You have 4 hydrogen here. We have to put 2 here. And now please always leave oxygen just at the end. You have 6 oxygen on the right hand side, then you should have 6 on the left hand side. You should put 3 in front of the oxygen molecule. So what can I tell you about this reaction? First, 1 mole of ethylene reacts completely with 3 moles of oxygen to produce 2 moles of carbon dioxide and 2 moles of water. Or you can say the molecular weight of this ethylene is 28 grams. It combines with 96 grams of oxygen to produce 88 grams of carbon dioxide, and 36 grams of water molecule. Now look at them. When you sum these masses up, you see that they are going to be equal to each other. So this is the law of conservation of mass. But when you look just upside, when you just sum these up, the mole numbers also, in this case they are equal, but they may not be equal for all types of equations. This is just a coincidence, just be careful. Now I write their mole and mass relation. I can use both of them. For example, 1 mole of ethylene just reacts with 96 grams of oxygen to produce 2 mole of carbon dioxide and 36 grams of water molecule producing. What else? I can have 4 different properties, like 1 mole of ethylene reacts with 96 grams of oxygen, which produces carbon dioxide containing 6 moles of atom, and with the water produced at STP, let's say 44.8 liters. So this is all about the direct ratio. If you just form your direct ratio properly, you're going to have the correct answer. Now let's look some common examples. When aluminium is heated with sulfur, aluminium sulfide is formed. Now here is, we are going to write the reaction and balance the reaction first. A. You have aluminium plus you have sulfur, and it produces aluminium sulfide. Now how do I write the formula of this compound? I have given you their group numbers here, so you know their oxidation numbers, and you're going to make that crossover. So please balance the equation, put 2 in front of aluminium and put 3 in front of sulfur, and A is done. Now comes B. If I have 6 mole of sulfur, so how many moles of aluminium do I need? So this is again a direct ratio. If this is doubled, this should be doubled also. So the answer will be 4 moles. And C, if there is 0.4 mole of aluminium used, then how many moles of aluminium sulfide is produced? Again, the direct ratio. In this case, you can look it as from aluminium to aluminium sulfide, there's half in here. So you can take the half of this value and find the answer as 0.2 mole of aluminium sulfide. Another example. There's a reaction already balanced, and you have some unknown elements like X and Y. Now first I'm writing the reaction all over. It says you have 3.2 grams of X oxide and combining completely with 3.7 grams of Y hydroxide to produce 6 grams of YXO3. Now what is missing here? The mass of water is missing. So what you have law of conservation of mass. So you're going to just equalize them like this. So if you like to find the missing mass, this is going to be 0.9 gram. Okay, now the first step is done. It says calculate the atomic masses of X and Y. So in order to calculate that atomic mass, I need their mole numbers. So of mole number of which one I can find it? I can find the mole number of water here. Now if you calculate it, 18 grams of water is 1 mole. So what about 0.9 gram of it? This is going to be 0.05 mole. So I'm writing on the top of them. If this is 0.05 mole, this is also will be 0.05, this is 0.05, and this is also 0.05. So I can have my ratio now. I can write it as 0.05 5 mole is 3.2 grams. So what about 1 mole of it? This is going to be 64 grams. Now in this one you have 2 oxygen atoms. When I subtract the oxygens, you're going to end up with 32 for X atom. So comes this one. 0.05 mole of Y hydroxide is 3.7 grams. So what about 1 mole of it? This is going to be equal to 74. So 74 minus 2 hydroxide, which is 34. So Y is going to be 40 here. So X is supposed to be the sulfur and Y is supposed to be the calcium atom. Aluminium and hydrogen bromide react according to the following reaction. If 4 mole of aluminium and 9 moles of hydrogen bromide are allowed to react with 100% yield. Now the meaning of 100% yield is one of the reactants, at least one of the reactants should be consumed totally. So just writing all over the reaction, 2 aluminium plus hydrogen bromide giving you 2 aluminium bromide plus 3 hydrogen. When you're given a reaction like this, before starting the calculations, check that whether it is balanced or not. Now in this case, this is not balanced. When you put in front of 6, then it is going to be balanced. Now I have my initial values: 4 moles of aluminium, 9 moles of hydrogen bromide, and in the beginning there is no product here. Then 9 mole of hydrogen bromide is consumed, then 3 mole of aluminium is consumed, plus 3 moles of aluminium bromide is produced, and 4.5 mole of hydrogen is produced. So when you finish with the reaction, you're going to have your final mole numbers. 1 mole of aluminium is going to be excess. You have done with the hydrogen bromide, so this is your limiting reagent, and you have 3 moles of aluminium bromide and 4.5 moles of hydrogen. Now when you do that table, probably you're done with all the questions. For example, A, which one of the reactant is the limiting one? So this is the answer of A. How many moles of excess reactant are left at the end of the reaction? This should be B. What is the mass of the hydrogen obtained? Now this is C, but with one more step. If 1 mole of hydrogen is 2 grams, what about 4.5 mole of hydrogen? This is going to be 9 grams. Next one is a combustion reaction, a mixture problem in fact. You have 0.5 mole of mixture containing propane and ethane gases. When you burn them, 1.6 mole of water vapor is produced. So the question is the mole percentage of propane in the mixture, in the initial mixture. So if you have 2 substances to be burned, you should be able to write 2 combustion reactions and balance them correctly. So first propane plus oxygen will give you 3 carbon dioxide and 4 water molecule. So you should put 5 in front of oxygen. Now comes the ethane. Ethane, again burnt with oxygen. You have 2 carbon dioxide and 3 water, and I'm going to put 7/2 in front of the oxygen. Now the mixture is 0.5. So if this is X moles of propane, this is going to be 0.5 minus X. So what about the water in terms of X? It produces 4X mole of water. So when you triple that value, this is going to be 1.5 minus 3X. So sum of these two numbers should be equal to 1.6 mole, the question says. So when you get X from this equation, this is going to be 0.1 mole. So you have found the mole number of propane. The next step is the last step. In 0.5 mole of mixture, you have 0.1 mole of propane. What about in 100 moles? And you're going to end up with 20%. Now this is the last question. In this last question, you have no 100% yield. That's why the question is based on the percentage yield of the reaction. First, write and balance the reaction. Hydrogen plus nitrogen giving you ammonia. So when you put 3 here and 2 here, they are going to be balanced. Initially, you have 6 mole of hydrogen, 1.5 mole of nitrogen, and let's say that no ammonia. Now first, please forget about this 2.4 mole. So what would it be look like if this is 100% yield? In this case, probably all of the nitrogen would be consumed, where some amount of hydrogen is excess and some amount of ammonia is produced. When you're done with the reaction, this would be your limiting reagent, and you have 1.5 mole of hydrogen excess, and you would end up with 3 moles of ammonia. Now just be careful. You're going to have 3 moles of ammonia if you just make this reaction with 100% yield. If you have 2.4 mole of ammonia, what about the new percentage yield? This is going to be 80%.